All right, so I know that I've dressed up for these things in the past. Let me make sure that my screen is not. It's probably fine. I know I've dressed up in the past. I am dressed up for the freshmen's Romeo and Juliet right now, so don't think anything special. The fact that I'm doing a stats video for you, although it's been a little while. I'm gonna go over the sheet from Thursday, and this you will find this video in a Google form. So I'm gonna ask you to reflect even further after this too. And please be thoughtful about that. Maybe take notes from this because it might be hard to go find this video again unless you're good at copying videos somewhere. But, let's give this a go here. I'm going to start at the second part because we've all seen my video. I've watched it a million times. And we're going to use StatCrunch to simulate what basically me doing that experiment many, many, many times. That's what probability is. We're going to find what's the probability that I got 34 out of 50, assuming that I have an 85% probability of success. So what should have happened is you were going to get some bars that would form kind of a skewed normal curve. And the only reason why it was skewed to the low side was because of this. Number one was that basically I was lying about the 85%. But also that 85% is pretty high on the scale of percent. So there's just not enough room over here to get above 100%. Okay? So these bars were high because if I'm an 85% putter, then most of the time I'm going to get 85% of 50. That's what these bars mean. But what we found out was down here we were in the red zone. All right, and that red zone is that probability. That was the number of trials, the number of experiments out of 50 that I got 34, assuming that I have an 85%. And that's what I believe I'm going to write right here. In our sheet, interpret the meaning of the number labeled probability. Be as precise as you can. The probability that an 85, so that's me, an 85% putter makes 34 out of 50 putts is 0.000. It was low, wasn't it? Let's see. Can I go find it? Oh, if I was prepared, I'd already have it out. Well, there's the document. Can I go to here? Wow. So this was experimental 0.001. I think the legit. I will show you actually later what the actual answer is. Okay, but the sheet said 0.0018. This is crazy small. The probability that an 85% putter makes 34 out of 50 is crazy, crazy small. So that means this is wrong. 85%. That was a lie. So here, that's the idea of hypothesis testing. Someone makes a claim. Hey, that's me. Me. I made a claim. The claim was that Mr. Caputo makes 85% of putts. And then what I'm leaving out here is in those conditions, right? If you understand golf, I'm not always going to be 6 feet away in a perfectly flat cement floor. The statistician uses fancy language to assume this claim is true and propose an alternative that will take the original claim's place if we prove the original claim false. So that was a lot, okay? But if we show that this is false, we have to have something in place of that. Oddly enough, we can never prove the original claim true, because just because I collect one sample where I did come close to this, that doesn't mean that's true. That just means I can't prove it false. So there's going to be a lot of parallels with the justice system, if you will. I'll preface, I don't know when I'm going to talk about this more. I don't know if you've seen this Netflix documentary, Making a Murderer, as well as if you know the O.J. Simpson trial. Essentially, these are both about defendants trying to prove their innocence. That's exactly what I'm doing. I'm trying to prove my innocence but the evidence showed 34 to 50. That's too low, so I'm going to jail. So the null hypothesis is always a statement of equality. That's important. That'll be on the homework. So, but in this statement up here, that is equality. 0.85. Make sure I'm still recording. Good. The alternate hypothesis, notice I put in the less than. That's going to be a decision that you have to make about the situation. And sometimes the data will lead you towards that, will lead you towards a less than decision. But what's nice is that it's always the same number. So these always match. And this symbol here helps you with your statistical analysis. Okay? And if I just go back, that's why we were looking right here. This was a less than. Less than. Less than. So we were finding out what's the probability that, well, I actually have to update that. What's the probability an 85% putter makes 34 or less? Because it's more extreme. Like we tried to go over that back in maybe December. It's you can never find the probability of an exact event. It's always to one side of it, and we wouldn't want to go greater, because then, like, of course that, you know, this probability shows that of course I'm an 85% putter is going to make more than 34 putts. You want to go, what's the probability of that happening, or something more extreme? Determine the significance level. So this is your cutoff point. Like what, 0.0018 is tiny, but what if it was a little bit higher? What's going to be our cutoff? And that has to do with our confidence. It really has to do with confidence intervals, but it's slightly different. But it's the same idea. We've been using 0.05 the whole year, and this is the reason we were doing that. Was to learn this chapter. This is everything. This is it, people. So we set the significance level to be the probability cutoff for an event to be significant enough. In that case, we reject the null hypothesis. And hopefully you read that a couple times. It's 0.05 is that barrier that we would say, okay, below that, nope, I don't believe Mr. Caputo. Above that, man, then I kind of have to question myself. So look at the notation. Alpha shows up again. Fill in the blank to check your understanding. So if the probability of my sample occurring by chance is less than, because we want an extreme event, so the probability needs to be small, then we reject the null hypothesis. This word doesn't show up a lot in other contexts, but I think about it like in an experiment, almost as a control. I'm not a scientist, but it's more like this is what kind of the most basic idea is, but really the alternative is what we're going for. I don't know if that makes sense, but I think of the word nil too, which means none. It's like a starting point. All right, so now we're going to get into the calculation part of it. Confidence intervals, we're not going to do too much, but we learned it recently. So I wanted to show how it still applies. And it has to do with what I show you next. But remember, to make a confidence interval, we have requirements. And that's still so important. If you're going to run a hypothesis test to make some sort of big conclusion that somebody's lying, you got to make sure the requirements are met. So we need a random sample. And I bet there are people that would argue with me that those 50 putts was not random. It probably was. But I'll let you argue with me. We need all of the binomials. Because this is a proportion problem. Notice all the p hats and q hats. We need all the binomial requirements. So what are those? Fixed number of trials. I was going to do 50 no matter what. Independent. And this is a tricky one. Maybe you've heard of an athlete going on a hot streak. I made the first 8 putts. Maybe. Either way, there was some times where I was making a lot, so maybe I get confident, and I start going. Or if I miss one, then I take a break and think about how I can make the next one. I would argue that the trials are not independent, which is interesting. What's another one? There has to be just in or out, right? True or false, so it's either in the cup or out of the cup. And there's a fourth one. Fixed number of trials, independent. The probability remains the same the whole time. So yeah, it's not like I get better at putting or worse at putting as we go on. And then the NP and NQ. So number of successes, number of failures needs to be greater than 5. And in the beginning, both need to be greater than 5. In the beginning, when I started making a lot, I was like, crap, if I make all of these putts, then this fails. Then I had no failures. But don't worry, I failed plenty. Okay, P hat, 0.68. Q hat is 0.34. All right. N, I took 50 putts. Z for 75%, for 95% is 1.96. Remember, we don't need T in a proportion problem. We just use Z. All right, so to make the confidence interval, is there any room over here? Let's do 0.68 plus or minus 1.96. So we're doing Z times the square root of junk. The square root of 0.68 times 0.34 over 50. And I'm just going to go find Desmos and type that in. .68 plus 1.96. You can do square root 0.68 times 0.34 divided by 50. Notice I don't care about what the error is because it's all built into the confidence interval. So 0.18813. Yeah, I'm recording a video. 0.68. And then just change it to a minus. 0.547. Is the claimed P in your interval? Okay, so the claimed P, notice there's no hat here. So this is your population proportion. So that's what I claimed as what I was. So this is the null hypothesis. Is the null hypothesis in the P? Well, my null hypothesis was 0.85. 0.85 is not in here. Boom, this means we reject it. That is, I believe, how the confidence interval works in this case. We could have made the confidence interval not at 0.68, but at 0.85. But it doesn't matter because it's just taking that error and sliding up to 0.85, and now 0.68 isn't a part of that anymore. So it's really like, does your sample fall in the confidence interval based on your population proportion parameter or the other way around? Either way, we reject. This method over here is we're going to use